There we go. Correct me if I'm wrong, but I think you should now see the title page on your screens.
Yeah, that's good.
Thank you very much. Okay, so thanks again for the introduction, and thanks to everyone here for attending. It's great to see you all here. So just a little bit of context, we're doing something slightly different today. If you were joining us for previous sessions, you would have seen that we had our first one is a very high level overview of the whole process, taking Caliper data from importing all the way to a report. One of our sessions was really a deep dive into one of the processing modules. Today we're somewhere in the middle. So we're going to chat about 3 of the processing stages with the aid of real data and the help of one of the analysts in our team. So our hope is that this is it's a teaser session. You're not going to get absolutely everything you need, but it will prompt some thoughts and then perhaps some questions from you, and we can talk about those at the end of the session. As Marilio said, that poll should be live as well. So please, if you can get that, get some boxes ticked there. There we go. That's it. I think I can see it on my screen now. That'd be great. So as Marilio says, just to help us fine tune the content for next time so we can understand you guys better. So I'm going to just so we're on the same page, a little bit of an overview of where we're coming from. So ANSA Data Analytics, we're a team that's been together in one form or another for decades, over 20 years. We've got about 15 people, all specialized in the analysis of cased hole logging data. So our topic today is well integrity and specifically Clarity, the software that we use to process multi-finger calipers. But we are a team that process the full spread of cased hole logging data, from pulse neutron surveys, looking at the formation and reservoir, to cement evaluation, production logging, and so on. And I'll just touch on our little timeline here. So the relevant parts for us today are really the fact that we've been involved with multi-finger caliper data since the mid-90s and before, really. But that was when the first, one of our precursors to our today's software came along. We were involved with that from day one. We've been big users of multi-finger caliper software ever since then. And we're just from the last few years, the important stuff really is that ANSA was demerged, became a standalone company, and that allowed us to service more people. And Clarity, our topic for today, was we started development of that over the last few years, and it was released at the beginning of last year. And it's software that's in the hands of customers, operators, and service companies since the beginning of last year. So again, just to set the scene, make sure we're all thinking about the same thing here. What is it that we're looking at here? It's the condition of the tubing and casing in either your customer's wells or your own wells. And what is it we're trying to assess? So we're using the multi-finger caliper to assess for metal loss, damage, deformation, and deposition. It's a tool that takes radius measurements and allows you to describe the inner profile of your tubing or casing. It's been around for a while. There's no hiding that. It's a mainstay of all integrity logging. But knowing that, it's run with high confidence and frequency. So really, if you're looking at tubing integrity, it's kind of the place to start. So with Clarity, what we're doing here is one thing that hasn't changed for a while is the approach from the software side of the analysis. So it's really what we're about is making the task, enabling more people to complete the task as if they were the expert. It's the creation of an expert system, which brings us on to the next slide. So whenever you hear me talking about or Jay perhaps talking about a PRISM module, so within Clarity, wherever we're utilizing machine learning or artificial intelligence or other optimizations, we're really looking to create this expert system, which brings those benefits that are on the screen now. So if you're an expert, you're going to benefit from increased speed, knowing that you're getting the best results. If you're perhaps in a hurry, perhaps you're closer to the well site and the job itself, perhaps you're not as expert with similar pieces of software, and you're going to be guided through all the processes, knowing that you're not having to select those troublesome parameters that you don't know about. You don't have the expertise to actually choose properly. That's where PRISM modules come in. So we're drilling down. We're going to get to some data shortly, but to set the scene again, just a little bit in more detail, we're going to be looking, as an analyst, we're going to be looking at how to draw findings from processing, during the processing of your data, and how Clarity helps you get there. you have to be aware to some degree about the flow from importing your data into the software all the way through to getting a report. So this is quite good for giving you a bit of context. You can see that we're going to be talking about data processing in the middle there, where you see those arrows floating around. You've got some choices to make there. And that's, again, that's where Prism really helps you, as it can guide you through those stages. One stage, which is the first one we're going to talk about, is centralization. So I'll give you a brief description about that. But we'll also touch on what we call recalibration and something which is closer to the post-processing stage, which is Prism joint identification. We've covered the whole process in a couple of videos that we've got on YouTube. So just give our company a search, ANSA Data Analytics, and you'll find them. So centralization. So this is quite a big topic. So like I said at the beginning, it's going to be an introduction to the topic. But for the moment, if you just understand that the tool string that you have there, so that's what you're acquiring your data with, that tool string will be lowered into the well, and your well will probably have some deviation to it. So through natural, of course, the natural effect of deviation and gravity, your tool string will sag towards one side of the tubing. So on the right-hand side there, that demonstration there of the tool string being closer to one side of the pipe wall. So that's completely natural and expected to happen. So what's the problem there? The problem is that when you get data from the field, it's going to look like it is on the left. So we've added a color map. So just to demonstrate the fact that where you've got the blue values, those are the low radius values. And where you've got the green and yellows, those are the high values. So the low side and the high side. So the problem with that is you cannot assess metal loss. You can't take penetration values in percentage terms from data that is in that state. So you have to centralize it. And that's what the data looks like on the right. Now, how do you do that? So there are, again, there's a lot of, it's a bigger topic. But for the moment, if I was to say that you have to apply certain parameters, with legacy methods, you have to apply certain parameters to the process to get the best results. So on the left there, that's a color map of some radius values, and you've got some highs and lows. You've got some blue features there, which are which is deposition, and you've got some small high value features there as well. Now these are the things you're actually looking to assess, and these are the things that are actually causing you some difficulty when it comes to centralizing the data. So it's a bit of a double whammy there. What you've got to do is consider these points as what we call outliers, and then you've got to exclude them from your processing. Normally it's a compromise solution, so you're excluding the same number of outliers all the way through, or perhaps you're zoning it one or two different choices. But what we're doing with Prism centralization, and you'll see the benefits of this shortly, is we're making the best choice for you absolutely everywhere. So this is 2 feet of data on the screen. It's making the best choice every single data step. As a human, you couldn't even do 2 feet of data to this level of detail. So you can imagine what 10,000 feet of data would look like. And on that note, I think it's actually 10,000 feet of data that we've got for you on the next screen. Here we go. So here's where I get to ask some questions for a change. I'm going to, we've met Jay briefly. So say hello to the nice people, Jay.
Hello, everyone.
So when it comes to analyzing multi-finger caliper data, as Morelio said earlier, this is Jay's bread and butter. He does this pretty much every day. So Jay, I've just presented you with 10,000 feet of data, and you've been asked to describe the condition of it. So perhaps you could start with, just tell us what your next steps are, really.
Yeah, so upon import, this is a highly typical first view that we're going to get when we get data from the field. This is, I can already tell this is uncentralized data. As you pointed out, we've got a color map on the left-hand side. So the more green and red band down the middle, that would be the high side of the tubing or the casing. And then on the left-hand side, we've got, well, left and right hand side is the low side, where the caliper is more depressed on the bottom of the casing. On the right hand side, we've just got another representation of the caliper fingers. We would refer to this as the minimum, maximum, and mean track. So it just gives us at each depth frame our highest points, our lowest points, and the average. Upon first import, I'm making sure things like the color map is sensibly set up. And I've probably done this beforehand. So before I've even received the data, I've received a schematic and I've set up my project, and then Clarity will just automatically apply the correct color palette upon import. I'm checking things like the mean ID there. Is it close to the expected nominal? So was the schematic right, or is something going on, or that kind of thing. And then in terms of QC steps that I'm carrying out here, it's things like flat lines, auxiliary sensors, but most of the quality check steps are happening on centralized data, so you can view it a little bit better. So I centralized with Prism, and I think got another image here. Yes, so upon centralization, we can see there's a much more uniform color. This greeny blue, as I was talking about earlier with the color map, that's set to the nominal of the tubing. So green is good. The more blue values are lower ID values, and they represent restrictions of some description, either deformation or deposition. The more red values are higher ID features, of which we can see some on the color map, but predominantly on the right-hand side track there, we're seeing repeated high ID spikes. Now, from just my experience, I'm going to say that those are probably collars, and I think that is actually the case. However, there are real high ID features. So towards the bottom in particular, we sort of see a trend upwards on that high ID curve. And that's not consistent with what a collar would look like, because it's over too wide of a depth interval. Okay. So I think if we zoom in a little bit further, particularly on that bottom, I think we can see a little bit more of what's going on.
I'd be worried if my well had a hole in it every 30 feet.
Yes, yeah. It'd have to be perforated all the way through.
That's an interesting one. Let's have a look at let's have a look at what's at the bottom there. That's certainly of concern, I'd say. So we've got about, what's this, about 1,100 feet on the data. We've zoomed in now. Well, we can see a lot more detail, obviously. So yeah, let's just have if you could run us through what we've got here.
Yeah, so we've got two sort of sections of features, so to speak. So in the top section, we've got pretty prominent ovalization here, and so you can see this in both the color map and in the min, max, and mean track. And being able to differentiate this from true metal loss or true high ID features is very important. As a lot of part of my job is ascertaining which metal losses or which high IDs do actually describe metal loss. So there's two ways, or from both tracks, I'm ascertaining this. On the color map, we're seeing alternating blue, then red, then blue, then red, then blue. Through experience, whenever I see this, you already know that the blues are actually opposite each other. And it just takes a little bit of practice to get your mind in that space that difference between each section is the two low sides are opposite each other, the two high sides are opposite each other, which we all intuitively know that is what ovalization is. One of the diameters is larger than the other. And then with reference to the right-hand side track, we're seeing a separation in the minimum ID and the maximum ID. So they're separating away from each other at the same time, which is indicative of ovalization. Towards the bottom, that looks like true metal loss. And I think if we zoom in a little bit further, we would see more about the character of what kind of features we've got here.
Okay, yep, can do. So we've got some deformation at the top, and what we're hoping, well, I say hoping, what we're presuming to see is metal loss at the bottom. So let's have a look. So we've zoomed all the way in now to something like 170 or 150 feet on the screen. So we're getting a lot more data. Yeah, so it's just if you could just run us through what we're looking at.
Yeah, so two quite prominent tracks of metal loss here, which is obviously quite concerning. And then on the right-hand side, we're seeing they're smaller in terms of depth interval, but we're seeing certainly some holes there and some high ID features. In general, where that max ID curve is sort of floating between 30 and 50% on average, but some localized, much higher features as well. We are seeing a little bit of deposition as well. We see that both in the color map and in the min, max, and mean tracks. And certainly some below the drift idea of the whichever kind of casing or tubing this is. But that's maybe not the prime concern, I would say, from this.
Yeah.
I think, well, to talk to centralization a little bit here, the widths of the tracks are changing. So, sometimes we've got two tracks that are separated, maybe 5 caliper arms in width on one side and then another 5 on the other. And then sometimes we're down at one arm for a distinct feature. We've got highs and lows. So in terms of choosing your centralization method and choosing your outliers, you either need to find a happy medium based on your time constraints, or you need to do a lot of different methods and splice them together. So for the software to automatically choose at each depth frame how many outliers you're going to use is obviously very useful for increased accuracy with no increased time.
Gotcha. So I guess maybe to highlight that, we've got our next slide is looking at one single feature.
Yeah.
So drilling all the way down now into what we've got here, which is just quite a large penetration, but it's quite isolated. It's quite small. So let's think about this one in terms of like we were talking about there, the centralization issue that we've got here.
Yeah. So that feature is recorded by 2 fingers. So if we're kind of ignoring the deposition, which there's also present, so that's 2 outliers at least. Above and below that, maybe it's 0, maybe it's a different kind of outliers, because we refer to minimum outliers and maximum outliers, i.e. high features or low features. And that feature is, it's not even half a foot long. So that would be a splice at the top, a splice at the bottom, different centralizations methods for each one. Whereas Prism's just automatically done that. And that's achieved us a penetration of 91%. Yeah, so I think we should draw a comparison as if we didn't use Prism or we didn't choose any outliers, what would be the impact on the penetration itself?
Yeah, so this is, I think, quite realistic of some alternatives out there, some vendor alternatives out there that have a simpler option when it comes to centralization, or perhaps through lack of knowledge. If you were to not choose the right parameters, let's have a look at what the differences could be.
Yeah, so I think most concerningly, that's quite a significant decrease in penetration, which is always what will happen when you're finding a middle ground or you're not ignoring outliers for penetration features, is you'll reduce them. And that's almost 10%, which is, quite a significant difference. In terms of how I can tell that feature has not been centralized in optimum ways, either on the left and the right of the feature immediately, we're seeing a darker blue sort of patch. And that's an indication of me when I didn't have Prism, that's how I would tell that this feature needs to be centralized a little bit differently or a different number of outliers. But yeah, as we sort of highlighted before, to do this over 10,000 foot when the features are changing from 2 arms to 10 arms.
Yeah.
And yeah.
Okay. That's basically an impossible task. You've got to use your eyeballs to do that. You're not getting much help. So,
is it fair to say that here probably the analyst in a normal situation would at best maybe put 3 different zones in here, and even then,
yes,
it's probably not, isn't it? It's probably this feature will probably end up just being lumped in with whatever is above and below it, and then you end up with a reduced penetration.
Yeah, and the time constraints, you don't know the story of when this data was provided to, whoever analyzed it at the time, and if they needed answers yesterday, maybe you go with your first choice, and if it's good, but it could be better.
Okay. So that's again, that centralization as a teaser. That's comparing legacy methods with the ability to centralize data in the best way with one click, and doing it first time. we'll move on to our second topic, which is recalibration. So recalibration, so as an introduction to what it is, it allows the user to correct for various data quality issues, and it's distinct from tool calibration. So if you're familiar with running a multi-finger caliper, you know that it requires tool calibration in the field before you acquire data. This is recalibration, and this is done in processing. It's an optional step, as ideally your tool is perfectly maintained and calibrated, so you can avoid something like even having to consider something like this. However, I think in realistically, you are going to be presented with perhaps minor issues, minor sensor arm drift. Perhaps you can correct finger wear. Perhaps your tool calibration wasn't that good. Perhaps the wrong file was applied to the tool. So you can correct these kind of things with what is actually a soft touch approach with recalibration. Depending on what you've got, you can easily be half an hour to 2 hours if you're getting the right parameters. And that's where Prism recalibration comes in, where we can get good results without having to ask the user for various parameters. So I mentioned that word parameters. I think that's where Jay comes in and tells us a little bit of background about how recalibration is actually achieved.
I just firstly on that previous slide, I want to point out how it is that I can tell that something can. So as you said, it's not mandatory, but I would say more often than not, most data sets are going to benefit, a bit from a recalibration. In terms of seeing whether or not it's a good candidate, I mean, here we've removed the caliper finger tracks, and that's how most analysts will ascertain whether or not the data set needs to be recalibrated. And we're looking for what we call stripy data. So from this view here, you can see some stripes. I think most predominantly that one on the right-hand side, and that's higher, so it's more yellow, but yeah, so higher on average than the other fingers. Now that's concerning because high means penetration, right? So we want to try and kind of knock it back in line a little bit. And so, yeah, we can go to the next slide and I'll sort of discuss that. Yeah, so it's one of these things, again, you could do a 30-minute, hour-long topic on the actual ins and outs of the algorithms that are being used and the different methods and all that kind of stuff. But sort of as a high-level description of what's going on, the tool's already been calibrated. So the way I look at it is that each finger's had its own calibration, and you're kind of figuring by pointing the software at zones of data, you are getting an average calibration, and you're using that average calibration to inform how much a given finger is above or below the average calibration, and then sort of adding or taking away just a small amount to just bring it back in line. Now, if we look at like the scale there, it's generally speaking quite a small amount. So that's, a lot of them are 0.01 inches. But expressed as a penetration, it may be significant, or it's certainly noticeable.
Yeah, when the wall thickness is only perhaps 0.2 of an inch.
This is it. But yeah, I think the main takeaway is that even experienced analysts, you're probably going to have more than one attempt, and if you're inexperienced, it may take you half an hour, an hour. You may make it look slightly worse. Yes, it's just one of those things. It's to have it automated is appreciated.
So it's the selection of the good data, the zones, and the creation of these shift values that we're helping out, I think.
Yeah, because the things that can negatively impact it, if you pick a zone that's got a completion item in it, that's going to impact how well it works. If you pick a zone that's got lots of metal loss, lots of deposition, all of these things are going to throw off the recalibration. And just in terms of selecting zones and data and things like that, for it to just auto-populate a table with some zones, and then you click apply, and then it's done. You can move on.
Gotcha. So let's have a look at that example. I think, is it? We'll look at the same example from earlier. See how I managed to recalibrate this.
Yeah. So this is just I've I've clicked Prism Recal, I've clicked apply, and so like before and after. So I mean, I think that speaks for itself. It's completely smooth looking in comparison to what it looked like before.
Mm-hmm.
Beforehand, ARM 59, which is the more yellow one, 70% of cases of the highest feature per joint were found in that arm. And for that to happen is almost statistically impossible. This is 1,000 meters of data, and the tool is rotating slightly, which is normal. For it to be stuck in a track on one arm through the whole way up, it can't happen. Someone would have to be making it do that, and even I think if someone tried to get it to do that, I don't think they'd be able to. In terms of an actual reduction, ARM 59 was reduced by 6% in terms of the nominal thickness, so it's a 6% reduction in the penetration. So if we consider our last example, which was close to 10%, and then this is 6%, just between these two examples, that's 15% inaccuracy via poor or non-optimum processing.
Gotcha.
So yeah, pretty significant.
Okay. That's quite interesting. You mentioned the rotation there. It's another point. I think you guys are quite often using the tool rotation, which is a normal aspect of logging. Your tool is going to rotate as you draw it up the well.
Mm-hmm.
And to realize that having that track of penetration recorded by the same arm all the way up, it kind of sets alarm bells running. So being able to correct for that, it sounds like it's another good tool where we're helping with the creation of those parameters, so you don't have to have that in-depth experience. It's actually a really difficult task, isn't it?
Yeah.
I don't know if it was myself that taught you how to do it.
It was, yeah.
Yeah, okay. So you probably remember the phrase, this is going to be a little tricky. We'll get there. So,
yeah, it's just try it. Yeah, that's kind of the advice, is that because you can speak to what the parameters are doing and the actual like mathematics behind the algorithms, but basically you have to just try it repeatedly.
Okay. So that's recalibration. Great to see some questions on that one. I think it's an interesting topic. But we're going to finish off with, we're coming out of out of the actual data processing. So we've finished making sure we've got good data. We've finished making any changes. If we had to make any changes to it, we've done that. We're moving on now to how to get to these charts and tables. So we're thinking about how to actually convey the findings to our customers, to your customers, or to the operators. You've got millions of points of data over thousands of feet of tubing and casing. You really need to break that down into something visual, ideally. You need to extract some of the values from each joint of tubing, so perhaps the maximum penetration on each joint of the tubing, and that's how you then get to some of these charts and tables on the screen here, which allow you to see any trends essentially that you have. So how do we get from millions of points of data? How do we extract this from clarity, and just how important and how useful is it to both the analyst and the customer? That's my question to Jay.
Yeah, so I mean, it's completely, in terms of writing a report, like to write about millions of data points rather than 500 tubing joints, it makes it completely different. And to have tables and graphs and histograms. In terms of how we're actually getting there, in days gone by, it was an incredibly laborious process, probably the longest one, I would say. I think on the next slide, we've got a sort of more zoomed in. Yeah, so the objective is to isolate the connections and the completion items. And the reason we have to do that is because, most of the survey is the tubing body. We calculate our penetrations. Most of the time we calculate our penetrations based on the nominal IDs and ODs of the tubing itself. The connections are often higher. So if you don't omit them from your analysis, you're going to have these false high penetrations, which don't particularly mean anything because the ODs of the connections are higher. And so it doubles up as just being a good length to sort of split your data into. So in terms of giving data points, one joint is, this is max pen. It's just a sort of convenient deviation way to split up your data. And then in terms of completion items, in a similar way to removing collars, you know, that big red band in the middle of that completion item, that would be a hole, or it would, in fact, it would be quite an extreme hole, you know, because it's circumferential, this big thing, and that's not real. So you need to be able to split it up and sort of go from there. Now, in the past, this was done in a fairly manual, or even if you tried to automate it, it was done with thresholding and so cutoff values of if the mean ID moves by this amount, then it'll place a collar here, and then if you've got more than one tubing type, you've got to set up thresholds twice or 3 times, and if there's any features there, it'll put collars where you're not supposed to have collars and you have to remove them anyway.
So how are we doing it? Let's have a look.
Yeah, so we've got a video. Yeah, and I can't stress enough how much I love this.
Nice
the difference in time that it takes me.
So let's get it going.
Yeah, so this is a case where we've got more than one tubing size, and 2,000 meters of data, I think that was.
Yeah. So
we've joint identification, auto detect. We've set it loading for a little bit. And there we go. So it's done. I don't know how many colors is it put in there. Was it a little bit too 250 or so? Yeah. So, I mean, that in the past, that may have taken you several hours. And to be able to do that in 30 seconds or whatever that was.
Yeah, wasn't even that.
Yeah, and I suppose the other thing is that the amount of time that your collar selection would take in the past obviously scales with the length of the survey. This is not really the case for this. It doesn't matter whether or not it's 1,000 foot or 10,000 foot. It'll still take not very long.
Yeah, I think it wasn't even 30 seconds. I think it was quite a lot faster than that.
Or something.
We should have timed it. I should have gone through and done this manually, and then we should have.
Yeah, I think we still time, Jay. You can still have a go.
No thanks.
I think it's that what Jay was touched on there is where other legacy methods would ask the user for something. It's I need some help to find these connections. I need to use a threshold. Does it exceed a certain value, or does that sort of idea? Whereas Clarity's got a machine learning model running here that's trained on the profile of a connection. You know, what do connections look like? So that's the way we can actually just say, right, click auto detect, and we'll try and find them for you. And regardless of pipe size, where you've got 2 pipe sizes here, so the magnitude of that value changing doesn't actually affect the task, does it?
Yeah.
Yeah.
Yeah, it's purely shaped based. Yeah. It also means it's much less likely to mistake a feature, a MetaLoss feature, whereas before, if you're thresholding and it's just so happens something's happened, it might put a collar in. This is less. Well, in fact, that's the next example right there. There's MetaLoss on that.
Yeah.
On that high ID.
Yes. So there's an essential step as well. There's no getting around it. If you want to break your survey down into digestible chunks to actually talk about, you have to do it. And Jay rightly pointed out there, the longer it is for a human to do this, the longer your survey, it directly affects how long it takes to do it. Whereas you might be 6 seconds instead of 5 with Prism auto detect. It's a great tool. So it's glad to hear. Is there anything else you would like to say on joint identification, or is that us?
No. I think that's me on that.
Okay. So we're just going to wrap up now. Really, we've been through 3 of the Prism modules that exist within Clarity. Hopefully, we've given you an idea of the function of each of them and how they differ from other vendor options. How it helps the analyst. That's what we're trying to do. We're helping analysts, helping people who aren't familiar to the task operate the tool at the same level as an expert. So with that, I'm going to stop sharing my screen and we'll hand back to Marilio, and hopefully we'll got some interesting questions from the audience.